A big thank you to all my patrons who support the Engineered Mind podcast. Hi and welcome to the Engineered Mind podcast episode 69. In this podcast we cover topics such as engineering, artificial intelligence, neuroscience, life, and other interesting topics and fascinating ideas to educate, inspire and engineer people's minds all around the world. I'm your host Josef, and for this episode of the podcast I'm very happy to welcome Slawomir Polanski to my show. Slawomir is an engineer with a passion for numerical simulations. The master's degree achieved both in mechanical engineering and computer science fields made him realize that simulations are what he wants to do for a living. That's why he did everything to become a simulation engineer, and he is currently working in TECHNIA UK. He is also an author of the CoFEA initiative, which aims to popularize the usage of open source finite element codes. In this podcast, we covered bottlenecks when getting started with FEA, how to pursue a career in FEA, critical aspects of an FE simulation, the linear and nonlinear FEM approach, the democratization of FEA, and so much more. If you are an inquisitive scientist and thinker and want to learn more about upcoming projects, courses, and attend live sessions from experts in the industry and academia, register for free at community.sci-circle.com. To join my newsletter engineeredmind.sh with more than 1500 readers coming out every Sunday, where I share weekly science insights, visit josef.substack.com. And now, ladies and gentlemen, here's my podcast with Slawomir Polanski. Hey Slav, welcome to my show.
Hi Jeff, how are you?
Doing well. So today we have, as I already mentioned before the podcast, it's like FEA week. So I interviewed Lukasz Kaczmarczyk a few days ago. So today we have Slav on my show. We'll also talk about the finite element method and CoFEA, and also what is FEA and what's the difference between FEA, FEM, and how to delve into this beautiful topic. But before we jump into the crisp topics, can you tell us who are you, what are you doing, and what's your expertise in the field of FEA?
Okay, so my name is Slawomir Polanski, but people call me Slav. So my background is mechanical engineering and computer science. So I did bachelor's and master's degree at the University of Science and Technology in Krakow. Then I also did computer-aided engineering course, master's degree at the Cranfield University in United Kingdom. So when I graduated from Cranfield University, I got a job near Oxford in United Kingdom. The company is called now TECHNIA. So I'm essentially a simulation engineer. I'm helping people with like Abacus model, let's say, because the TECHNIA is the largest reseller of the source system software in UK. So we are selling the software, we are supporting the software, but we also do some consultancy projects. So some part of my work is to help people to build their models, to install Abacus correctly. So it's actually quite nice part of the job, because I talk a lot with people and I help them to do what they want in the software that they bought from us. And the other part of my job is the consultancy part. So I participate in some projects with like various industries. So let's say it can be automotive, it can be biomedical, like many various industries. So apart from that, I also do a bit of blogging. I also started the initiative called CoFEA, or I prefer to call it CoFEA, because it's easier for me to pronounce it. I'm very into simulation.
That's very exciting. We'll talk about Abacus because I have good memories about Abacus. I used it in my bachelor thesis, and all the kind of automations you're also interested in, because you're kind of an automation freak in Abacus, and we're not in your blog about this as well. Let's start very, very simple. So I usually ask every expert on the show how they would define their own field. So how would you define FEA or FEM in the first place, Love?
Yeah, so I think FEA is the most practical tool that can be used within a mechanical engineering field. So it lets people to understand how objects behave. So you could imagine you build something in CAD and then you don't know how that behaves in reality. So you import it to any FEA software and you run it and you can see it. So you can see how that behaves, whether it fails, whether something something wrong is happening with the object. So I would define FEA as the most practical tool for engineer, I guess.
When it comes to learning FEA, because there's so many different tools and what boundary conditions you can apply and so on, like if you delve into the FEA world, how would you personally get started? Is it like just picking any software and just jump straight into a project, or would you pick a project and then find a specific FEA software that's suitable for this project? How would you approach this?
Okay, so I think I will try to explain it based on my own experience. So I learned the most of FEA during my thesis. So the first thesis was the bachelor's one, and I was like investigating how the skateboard will deflect. So skateboard is made of some plywood. So essentially I was learning how the composites can be analyzed in FE software. So at that point I was using ANSYS, but the software really doesn't matter if you know what you are doing. So at that time I didn't know what I was doing. So I had to learn everything from scratch. I had to understand the physics of composites, and then I was able to use ANSYS properly. So I guess to be able to learn FEA, it's actually the best to start with some projects that you don't have to have much experience within the area, but it has to be a challenge for you. So you are actually open to something new, and that allows you to grow. But speaking of learning FEA, I think it has to be divided into 3 components, let's say. So FEA is not only about the methods or the software. So I would say it's like computer modeling. There is finite element methods, and there is other part of science that has to be learned. So the computer modeling, it's fairly easy, although it's fairly easy to learn when you've got access to the software, because it's only about finding out which button to click, and where are the settings, and how to operate within a digital environment. And then there is the finite element method. So it's essentially a mathematical concept that you need to figure out. And you could run FEA study without knowing what's the finite element method, but it's like driving a car on a first gear all the time. So it's really hard to do something more in any software. And then there is also this other science bit. And I think it's actually the most difficult to understand it, because you've got mechanics, you've got strength of materials, material science, thermodynamics, everything together. And it's actually not that easy to connect the dots between some part of science, some equations connected to finite element methods, and then connected to any type of software. If you have some experience, then it's actually, if you've got some experience with science, then it's not that hard to move to finite element software, I would say. But if you start from scratch, then everything is new for you. And sometimes you just need to learn something, I would say, by heart, and then you will start seeing the connection between the dots. So I would say, yeah, it could work this way.
Yeah, when you think back about your first FEA project, on skateboards or your thesis, what were the biggest bottlenecks when you delved into the field of FEA? Was it more boundary conditions? Was it more understanding how the software works? Where do you see the biggest issues for beginners or maybe intermediate users?
Yeah, so I think the largest bottleneck in learning FEA is that it's being taught rather on with theoretical approach, but it's very practical tool. So when I started learning this, I had to understand the composites, and then once knowing the theory of composites, then I had to learn how to define it in ANSYS, and it wasn't that easy, because at that time there were no YouTube tutorials. It was very hard to find something. Also, like, I learned everything in Polish, so then I had to change my mind to read everything in English. But that was actually a good choice to start using English only. So figuring out how to use software to model something that you know only the theory of it, then it's not an easy process. So that would require more either access to some expert that would help you to understand or where to click, or like spending a lot of time in the documentation, reading something and then trying to like apply it in a software and see if that works. If it doesn't, then you need to search for different things and try to apply it once again. But I guess that's how learning works. So you need to fail to be able to grow. So
yeah, that's right. And when we talk about the FEA career, because a lot of people on LinkedIn asked us, like, if they want to pursue a career in FEA, what path should they take, or like to get the most successful as fast as possible, let's put it that way. But also when it comes to the highly competitive field of FEA, how do you would personally, like, what tips would you give them if they want to pursue a FEA career? What would you tell them? Like, is it even possible? Is it too competitive? Or is it like that FEA might eventually vanish? I'm not asking you for any future predictions here, but when we think about AI, artificial intelligence, will it even become like redundant to be an FEA engineer? What would you say?
So I don't think that engineers will become redundant at any point in our life.
That's good.
I hope so. And I think it is the case that if like FEA is only a tool, so if you've got some experience with like physics, mechanics, or any engineering field, then you can learn different tools to be able to solve the issues that you experience, and to be able to start working as a simulation engineer, I personally had to move to United Kingdom because I wasn't able to find any proper job in Poland. But yeah, I moved there. I was fortunate to get the job there. And if I were to advise someone what to do to start, then first of all, you need to understand, like in terms of FEA, someone would need to understand this, like mechanics and material science, and then try to even like run some tutorials in any type of software. Like, I would not advise to pick a particular one. Like, any type of software is good. So there are plenty of student versions of Abacus or ANSYS that people can use and learn something new. So I would start like solving some tutorials, or it's actually better to start solving benchmarks, let's say, because if you solve benchmark, then there is no like described way on how to solve it. There are some boundary conditions, there are some loads, there's the output that you need to like the output from the simulation and the output from the benchmark must match. So I would start, I think, with benchmarks to learn learn FEA once again. And then I would probably say that soft skills are also important when you try to sell yourself to potential employer. So yeah.
Very good tips, Slav. I appreciate it. You also mentioned boundary conditions now, Law. From an expert perspective, from your own perspective, like when you apply boundary conditions, do you think this is the most critical aspect? Because I talked to Lukas Skotny on my podcast about boundary conditions, and he thinks that boundary conditions are one of the most complicated things to actually understand. Because, well, you kind of mimic the real world, but you kind of have a model, and model and real world never match because every model is wrong, but some are useful, as we know. How do you personally approach boundary conditions in the first place? Do you have like a special method or methodology how you approach this kind of problem?
I wouldn't say that boundary conditions are the most, they are the most, they are very tricky, but there are plenty of other things within the modeling concepts that you make a mistake and like there is no way to avoid it. So for example, you've got some material data, and if you model steel or aluminium, then that's fine. You've got some Young's modulus, Poisson's ratio, you type it and that's fine. But there are different materials like rubber or composites that it's very hard to find appropriate material properties. And then like sometimes you have to spend a lot of time searching for articles that may contain a particular property. And even in that article, the property might have a wrong unit and your analysis will fail. So that happened to me actually. But yeah, in terms of boundary conditions and loads, so what I'm usually like performing some kind of sensitivity study. So I'm trying to find out how a particular boundary condition or load will modify the results. So if I see that something is very sensitive, like any change will change that drastically the results, then I basically like try to contact the customer, talk with them, and like I ask them how they see it, like what they see in the real behavior. And then like, step by step, I try to replicate the same idea, the same behavior in the simulation. Sometimes it's like unavoidable, like you cannot avoid using contact. You have to model the whole object like assembled together, and it's like no way to actually replace the contact with some boundary condition or load. So yeah, sometimes if there is no way to simplify the model, then I try to make it complex, see how that works. And if I really need to run simulation faster, then I will try to, based on the complex model, I will try to create some boundary conditions that will reflect the behavior of the more complex model.
Yeah, very insightful. So let's stay at simulation, or at the simulation part for a few more seconds or minutes. When it comes to deciding whether I pick linear or nonlinear FEA for my specific simulation, this is like a common question that people have. Like, should I pick should I do a linear or nonlinear study? How do you personally approach this? And are there several other questions that you ask yourself in the beginning when approaching? Like, you have a brand new case, you don't even know what's going on. What are the questions that you ask yourself on how to approach this case?
So personally, I think most of my models are nonlinear because in reality everything is nonlinear. So Abacus is actually quite good. So like I work mostly with Abacus, and it's very good solver for all the nonlinear behaviors. So if I start like working on something, then first I need to know whether the material will be nonlinear. If it's not, then I will keep the solution linear. If it's nonlinear, then I will also temporarily use like linear material properties. So what I usually do is build a model which is like as simple as possible, and then I will add some complexity to it. So I start usually with small rotation, small displacement, linear material, and like no contact if possible. Then I will add the large rotation and large displacement bit to find out how that affects my computational time and also the response of the model. And then I will try to add probably different bits because when you've got like huge assembly, then you add one part, then you add another one, and step by step. And then once the large displacement and large rotations solution is working fine, then I will probably add the contact, which will make like the model highly nonlinear. And then probably at the end I will also add plasticity to figure out how, like, because if we add the plasticity first and then we add the contact, then we might get some issues. So I personally try to put the material nonlinearity at the end, but it's really case dependent, so it's hard to say. But I guess there is no rule in terms of like how to predict whether something is linear or nonlinear. I try to think that everything is linear and assume so, basically doing my modeling.
I see. We talked a lot about simulation right now, but a lot of people struggle to even have access to simulation tools in the first place, whether it's now Abacus. Well, there are student versions, same as with ANSYS and other tools. How do you see the aspect of democratization of this technology, namely FEA? I think you have a strong opinion on that, maybe a weak opinion, I don't know, but maybe you can get a little bit into depth here how you think about democratization, and is it even like the right term to use, and do you think we move towards the democratization of FEA?
Okay, so I don't really think that the democratization is a right word, because democratization should be for free, and it's clearly not, but that's not the point of the conversation. So democratization in the simulation world is basically like some companies, some vendors are trying to let more people use the software. So there are different approaches to that. So one way to do it would be to embed some simulation software in CAD software so the designers can use it. That's fine when the simulation software is good enough and simple enough for the designers to use. So I had some experience during the university that the CAD software had like very simple FEA solver, and that FEA solver did like, it actually, the results of it were very wrong compared to ANSYS results. So yeah, you have to be quite careful about it. But it like, I don't try to say that all the CAD embedded solvers are wrong. Like, for example, 3D Experience have Abacus solver now. I know there are some ways to, I think, introduce Nastran into Inventor, or SolidWorks has the Cosmos solvers. So it's definitely the case that it's going in the right direction in terms of the quality of solvers, I would say. And there are different aspects in terms of how to, let's say, give the software to potential users. So I know that there are different licensing schemes. So there will be like separate apps for particular users. So that can be quite useful, because it can be the case that if I'm working on, I don't know, structural analysis of some building, then I might not be interested in analysis of rubber, for example, I don't know. The other way to democratize it that people like the vendors see is to use templates. So I think that's quite a good one. So some advanced user create templates and then give it to less advanced people, less advanced engineers. And in this way, it's actually the risk of incorrect solution decreased. So that's good. And I think that the latest technologies like cloud computing can be actually very good for the democratization. So yeah, like people will have access to the hardware that they cannot afford, so they will probably pay some amount to run the simulation faster, probably with more elements, with like more complicated material properties and stuff like that. So for FEA, it might be the case that you can afford buying a PC that will run your analysis, but I guess for CFD, like you need to have access to proper cloud or HPC to run quite complex simulations.
That's a good point that you mentioned HPC. Do you think also for FEA applications that moving towards the cloud, let's mention, for example, SimScale in this case, do you think these are like promising solutions for the future? I mean, I'm a bit biased here because I work for SimScale. What do you think about it personally, like moving towards HPC systems?
Yeah, so I don't really know how SimScale is working in terms of HPC. So it's like a cloud solution as well?
Yeah, cloud solution, exactly.
Okay. Yeah, so I think like all vendors will try to do it. So someone may think that that's the only way to move forward. So everything will be on cloud, and like you will have access to everything from your mobile, from your laptop. But in terms of computations, like I said, I think, yeah, it's definitely desired. So you have more resources to run your job. You will be able to perform optimization studies, design of experiments. So you run a number of iterations of the same model, and you probably cannot do it the same on your own PC. Yeah, I think it's really good that something like that appears on the market, because something new always brings potential users, and I'm really glad when new users start using CAE software, I guess. So,
yeah. See, talking about the initiative, you mentioned CoFEA or CoFEA. What's this initiative about? Like, what does it actually stand for, and how can people even participate in CoFEA if it's possible?
Yeah, I think so. I'll bring the whole story. So from time to time, I'm basically asked, like, Slav, what do you do for a living? So I'm trying to say, yeah, I'm an engineer. Like, and some people say, like, what do you do? So I'm trying to say, yeah, so I create simulations. Like, what is it about? So I'm asking, like, do you know what CAD software is? Like SolidWorks, AutoCAD? And they said, oh yeah, I know what CAD software is. So then I'm a bit frustrated because they know what the CAD software is, but they don't know what the simulation software is. So I decided to do something about it. So my first thought was to create some videos about simulations, put it on the internet so people will recognize it, like what it is, what it can do. So when I wanted to create the videos, I was not able to do it because I didn't have the proper license, resources and stuff like that. So I decided to start playing with open source software to find out what it can do. And I've checked it, and it looks like it has some potential. Like if you know what you are doing, then you can do quite a lot with it. So I decided, instead of creating the videos, I decided to create some kind of initiative to let people know about the software that exists. It's for free, and they could use it to solve their own problems. So CoFEA stands for Cooperation and Finite Element Analysis, because I would like to create some kind of Wikipedia which shows how you can install the software, what is good about this software, how it solves particular issues, and whether I think that's the most important thing about CoFEA, whether a particular software can actually solve the problem. Because it might be the case that you use some software, you spend weeks working on it, and it happens that it cannot solve it properly, because the open source software is not as reliable as commercial software. And I totally understand that commercial software is better in terms of quality. That's why we paid for it. And that's why we received some support. In terms of open source software, there is no support. So for people who cannot afford buying commercial software, it doesn't mean that they cannot innovate. They cannot check some structures. They can still do it, but they might need to use open source software for that. So within the CoFEA, initiative, I try to show how this can be done. So there are plenty of softwares, like, for example, Calculix or OpenFOAM, that's CFD code, and I'm trying to focus only on the FEA bit. But it's still there. It's Elmer. There is MoFem. And yeah, there are like many codes, and some of the codes actually have some like capabilities to connect to each other. So within a CoFEA, I also try to show how you can use the best part of a particular code and send it or export the data and import it to different software. So for example, we try to create mesh within Salome Mecha, but sometimes we prefer to use Calculix to run something. So you can export it as UNV file. Then there is some converter which is available on GitHub. You can download it. You can basically change the mesh extension to be like formatted correctly. Then you import it into Calculix and you run some kind of study. If you are a Windows user, then you can use Prepomax, and yeah, you can do similar stuff with that. So yeah, and for me, it's kind of entertaining to play with it, because when you've got access to commercial software, you see like some action may take 5 minutes, and within open source software, it may take 2 days to do the same thing. So it's actually for me to learn something new as well. So, but apart from that, the CoFEA initiative is set up in a way that it allows different users to contribute to the documentation, to send some new benchmarks, new results from benchmarks. So I use mostly Calculix, Elmer, and Codeaster. But I talked with Łukasz Kaczmarczyk from MoFem, and he contributed as well. So yeah, that's very good. Like the community growth. So yeah,
that's
I really like it.
That's so cool. Even seeing like the same people that we know contributing to CoFEA, so that shows how small the FEA world basically is. You talked about CoFEA, and some people might ask, okay, what's not CoFEM, for example? And this brings us to the point of what's the difference between the naming conventions, let's say FEM and FEA? How would you define the differences? Is FEA more used in industry? Is FEM more like pointing towards the theoretical side of FEA, FEM?
Yeah, so I think the difference is that finite element methods is rather a mathematical concept, and the finite element analysis is like a procedure that you apply within industry, I would say. So finite element method, it's kind of numerics, some kind of solver that solve the equations. But if you've got a problem in your factory, then you not think about equations, you think about the problem. So you will probably use finite element analysis to solve the problem. So yeah.
Cool. Is there any closing remarks from your side before we jump to the question rampage? So I've prepared for almost every guest 10 questions, which I ask you. Optimally, you answer them in 1 or 2 sentences. It's about like personal questions and FEA questions. Is there any last words from you maybe about CoFEA, how people can join, or where can they find CoFEA?
Yeah, so people can find CoFEA on my GitHub, or you can contact me directly. And if you want to contribute, then I guess you can either also contact me, or if you've got some like nice benchmarks or even like real applications, then you can send it to GitHub, make a pull request, and yeah, we'll do something about it. I need to also say that at the moment I'm very busy with other things, so I treat CoFEA as a like hobby project, and I try to do something about it whatever I can. But it happens that time is not a rubber, so we cannot like extend it. So yeah.
That's a good. I have to print that one on a shirt. Like time is not a rubber, so that's good. Time is not hyper elastic. something like that.
Yeah.
So I'll ask you the 10 questions now, which is the question rampage, and then at the end you can give your like additional thoughts on maybe FEA and last words from Slav on FEA.
Okay.
So the first question to you would be, Slav, what are you most proud of?
Oh, there are a number of things. So I'm quite proud of that I finished the degree in engineering. I'm quite proud of the thesis that I wrote. So actually 3 of them, so bachelor's and 2 master's theses. I'm quite proud of the fact that I moved to UK and started the job there without like knowing anyone. I'm proud of the fact that I'm working in a team. Like people in my team, they are like super brains. Sometimes it's just, I feel so small when they talk about things because they are so experienced, and yeah, I'm very fortunate working with them. Yeah, there are plenty of other things, I guess some more personal as well, but yeah, I would keep it for myself.
Okay, very good. I love the answer. Question number 2, what was your biggest failure and what did you learn from it?
Oh, that's a tricky one. There were so plenty of like failures that's hard to pick the biggest one. I would say not believing in yourself when needed. So for example, I was working on master's thesis and I was learning how to use Abacus and like I ran some models and they looked okay. Then I basically searched for different articles about the same topic because I was working on FEM and the fracture mechanics. So I found some articles and I tried to replicate them. And when I did it, like all the results, like they did not correlate with what was presented in the article. So it turns out that the article was wrong and I was correct.
Oh.
And I spent like 2 weeks like trying to understand, like what's happening here? Like I did everything as presented in the documentation of Abacus, and it's still not showing the right results with the article, but a simple model that I run, it like correlates well with the analytical function. And then I realized that the author of the article, like the dimensions were incorrect and the units were incorrect. So yeah, so that was one of the biggest failures, I guess.
I see, but also a big learning moment, I guess, for you.
Yeah. I guess since that time, I'm always assuming that I'm wrong, but then I'm trying to prove myself that it's not the case. And yeah, at that time, I always thought that I'm wrong, like that's all. And now I'm thinking not like it's a different way. So.
I know exactly what you mean. Question number 3, what advice would you give someone wanting to be as good in FEA as you are?
Try to be curious and learn everywhere, and try to, even if you read something that it's not really related to your topic of interest, then you will still learn something new. So I try to follow like plenty of people on LinkedIn, on Twitter, and it's not exactly sometimes related to my background. It can be related to, let's say, I don't know, AI or deep learning and stuff like that. Mm-hmm. But it's still nice to see like some connections between their ideas and mine ideas. So as much information as you can like get and operate on it, then yeah, it's very valuable, I guess.
Mm-hmm. Very interesting. Question number 4: if you could spend one day with a celebrity, who would it be?
That's a tricky question. I don't know. That's an honest answer. Like my first thought was Catherine Zeta-Jones, but probably like 20 years ago. No, I don't know.
Okay, it's also an answer. Question number 5: project you enjoyed working on the most.
Oh, there are plenty of projects, but I'm not sure if I can talk about it. So that's one of the main issues about finite, like working as a simulation engineer. There are so many interesting projects that you could talk about, but then you really cannot, because it's like sensitive information. But I can say that the FEM thesis was very interesting. It was a challenge. So if you're a student and you are thinking about your thesis, make it a challenge. Because it will pay back. So within the thesis, it was actually nice to see, like, it was a simulation of a gear, and there was like a crack just at the bottom of a tooth. So it was quite like, it was propagating, and it was not only like visually nice, but it also correlates well with the laboratory results. So I was able to predict how long the gear can operate, like in terms of time. So I would say it would like three months, and it will break. And someone did the same experiment in laboratory, and I did it in Abacus, and like there was the exact match. So despite the fact that FEM is quite new technology, but yeah, it was giving the right results. So yeah,
very interesting. 3 most influential people in your life. You can also skip the question if you want, if it's too personal.
No, that's fine. It's definitely my family, so I would treat it as a group. Definitely my team. As I said, I'm very fortunate to work with them. Well, I guess like there are a number of people. Like I already like named the groups, not not a specific person. So yeah, my wife, my parents, my brother, and people in my team. Yeah, I would say that.
Question number 7: favorite movie.
Armageddon, Independence Day. Like these are old ones. I know. Lord of the Rings. Hobbit wasn't that good. I also like Marvel movies, so Spider-Man, Thor, stuff like that. So yeah.
I made a joke when Dominic Madier was on my show saying Matrix, because FEA and Matrix, it correlates a bit. But then I brought the joke already, so if someone listening to the podcast is like, okay, again the same joke, Yusuf, I'm like, okay, whatever. Question number 8: if you would have one tip for people who want to pursue an FEA career, what tip would that be? Like one tip. Still curiosity or something else?
Yeah, I think it would be curiosity. Because if you are not curious and you have no ambitions, then there is no point of doing anything.
That's correct. Yeah, love it. 2 last questions. Number 9, because you talked about Marvel movies, so that's kind of funny. One superpower you would like to have?
Oh, yeah. There are so many of them. Is it only one?
One superpower you would like to have?
Yeah, I think I would like to have the power. Like, have you played Max Payne game at some point?
Yes. The first one.
Yeah, so I would like to have like the focus time.
Oh, yeah.
So at one moment, you just focus on one thing and there is no other distractions, and the watch doesn't move. So yeah, I would use this power.
That's a good answer. I like it. And the last question: if you were a superhero, what would your name be?
Once again, sorry.
If you were a superhero, what would your name be? Can be FEA related, like I don't know, Crackman or something like that.
I think I would use my nickname from internet. I usually use it, so it's called Spike, and Spike because Have you ever played Ace Ventura?
Yeah.
So he got like a little monkey, and that monkey is called Spike. So I would call it
Okay.
Spike.
I see. Okay. Now I get the connection. Cool. That were all the 10 questions, Slav. Thank you so much for giving us insights, also a bit about the personal life, and so people can learn more about who is Slav and not only about like FEA. So I think it's very, very important in a discussion like this. Are there any closing remarks from your side? Any last words on FEA? Any last words to the audience?
Yeah, so I think, I can close the podcast with what I learned about building models. So if you were to build model, always start make it as simple as possible and then make it more complex. Write a plan on how you will build it. It's definitely a lot easier to debug your model if you do it step by step instead of like building everything at once and then trying to figure out what went wrong. So that's the idea. I would also advise people not to use functions that they don't understand. So one thing in Abacus, for example, is the stabilization. So I'm always imagining that you put your model into the honey and there's like high damping. No matter how many like forces you put on your body, it doesn't move, it doesn't like deform. I would also advise people to do hand calcs.
Mm-hmm.
So I guess that rule can be called everything can be a beam if you are brave enough. So yeah,
That's good.
I guess that's my motto. And the final sentence would be always assume that you are wrong and try to prove that you are not. So,
yeah, that's a very good one. And also maybe last thing from my side, because we talked about this before the podcast, if you can automate something, automate it, right? Because you're also an automation freak and you did a lot of automations with Python for Abacus, right?
Yep.
Do you have it on your blog, some kind of scripting tips for Abacus in particular?
No, we actually, in my company, we actually do some training about Pythons, and there are some plans to create some blogs about scripting in Abacus. But I learned scripting in Python within 1 month. So there was like Code Academy. So if someone wants to learn Python, I had the background in C++ and C, so it was a little bit different than starting from scratch. But so I started on Code Academy, and then if you would like to use Abacus for scripting, then there is the whole chapter in the documentation on how to start, how the Python API works in Abacus. And I think there's the gentle introduction on how to do it step by step, and it's not that hard to learn it on your own. So
yeah, very insightful. Thank you so much, Slav. And I think scripting is very essential because when I had my bachelor thesis, it was about topology, 2 blocks sliding on each other, and then seeing if the elements would break or the aspirates would break. And then you could have a Python script saying, okay, turn the block clockwise or counterclockwise. So you don't have to do it in Abacus, which was kind of cool because you could do it with 1 click. So that's really, really cool if you can automate stuff with Abacus. So with that being said,
I think I think scripting gives you a very different perspective on the simulation. So I was thinking about it the other day and how to explain what scripting does for the simulations. And imagine that you are engine manufacturer and you've got number of engine designs, for example, and then you run one simulation of an engine and you've got, let's say, the piston which goes up and down in the cylinder, and the cylinder may change, let's say, the shape. So it's not the cross section is not a circular, but it can be oval. So if you are to run the simulation and you will see that it's oval, not a circle, but then how much the output from simulation will not be direct answer. So for example, you will need to write a script that basically creates like it finds the displacement on a circle. So then you will find out how much it deflects, and then that's fine. Like the simple answer is scripting is used to get a quicker answer from the simulation. But then if you've got number of the same studies of different engine geometry, then you can reuse the script and you will get essentially number of results in a second. And yeah, that's really powerful way to find out how to improve your design, because you don't have to do it manually step by step to find out how that behaves. You can ask Python to find it out for you. So
yeah, that's super exciting. So Slav, with that being said, thank you so much for the very interesting podcast. I learned a lot, and I hope hopefully the audience learned a lot as well. And every link to CoFEA or CoFEA, as well as your LinkedIn profile, I'll put it down in the description so people can reach out to you and maybe join the movement, however you want to call it.
Yeah.
So thank you so much, and I wish you all the best for the future, and we'll see each other, I guess, on LinkedIn or Twitter.
Yeah, thank you very much for the invitation, and it was nice to chat with you. So
thank you so much. Take care.
Yeah, bye.